equations of motion, where we looked at what happens if you have a momentum shift and the orbit changes for the particles. That's the basic one. We're going to look at the impact of this on longitudinal dynamics just for a few slides as the build-up to looking at RF cavities probably next week now. And then we'll spend the rest of the minutes or 45 minutes on chromaticity, which is the impact on the oscillations of a momentum shift of a particle, which I've not looked at yet. So first of all, we have something called momentum compaction, which is very important for consideration of RF cavities and accelerators. So we know that the momentum offset changes the orbit of a particle, and that's called dispersion. That's what dispersion is. So ideally, a machine with only horizontal bends wouldn't have any vertical dispersion. So a horizontal bend doesn't affect the vertical motion. It does affect the orbit horizontally, but what about longitudinally? That's orthogonal to horizontal motion. Is there an impact there? And the answer is yes, there is. It's a very, very important impact, because dispersion horizontally does generate a longitudinal effect by changing the path length of a particle through the accelerator and determining when it arrives at an RF cavity. So it generates a longitudinal effect because the total circumference of the off-momentum particle stripped around the machine is different to the reference particle, the total circumference. Now this matters for cavity dynamics. So we have to compute something called momentum compaction factor, and essentially is the correction to the path length or the circumference of a particle if it's got an orbit shift due to its momentum deviation. And this is extremely important lattice parameter. It's as important as the tune, so we should pay attention. So we have to essentially compute for a particle on a different orbit with a different momentum what the difference in circumference is. That's what the momentum compaction factor is. So we consider this situation where we have a dipole, a bend radius rho of angle theta, and the particle bends through the magnet. This line here is the design orbit, or the orbit followed by the design on momentum particle. All well and good. Now we know that we have dispersion accelerators, and the orbit followed by an off-momentum particle is different, linearly in momentum deviation to do some approximation. So we have some other particle coming in, and this follows this orbit, which is slightly different to the design orbit. It's a horizontal offset, and it's going to have a different path length through the dipole. So let's calculate what this is. So essentially, the difference in the path length of these two particles is the difference between this line length and this line length. So we just used approximation where theta is small, where the arc length is just L times the opening angle of the dipole, S equals r theta. So the length of this orbit through the dipole is just rho times delta, and the length of this one is rho plus x times delta, and we care about the difference. So if x was 0, this term would cancel this term, and delta c, the difference in path length, would be 0, but it's not. It's some finite value. So delta c, our path length deviation, is given by this. I've called it c, by the way, because we've considered a single dipole. What we'll do is we'll just assume the ring is made up of dipoles to compute an expression for the momentum compaction factor, which is just this quantity, essentially. So path length deviation is given by x, rho plus x times theta minus rho theta for the ideal orbit. So the path length variation is given by x times theta. So that's for a single dipole. The change in circumference of the entire machine would be adding up all these little path length errors around the entire machine. So a sum of all elements that would give us a path length difference. We write that as an integral, a closed integral around the machine, where we have x times theta. So that's x, that's the closed orbit shift of the particle through the element. Then we have d theta, which we write as ds times rho, where ds is a step through a dipole and rho is the relevant bend radius. So we just sum all these up, and if you just then assume it's continuously made of regions of some rho, where rho is infinite if it's a straight element, we can write that as an integral, and the circle is a closed line integral, meaning it's one closed loop of the accelerator. So we can calculate this quantity, and at this point, if we do this integral, where rho is wherever it is in a given part of the accelerator, ds is the length of that element, and x is the closed orbit shift for that particular particle, we haven't really said where the closed orbit shift has come from. It could be anything. So actually, this is saying that any source of horizontal closed orbit shift will generate a path length difference from the accelerator. But we're interested in a very specific source of closed orbit distortion, i.e. from dispersion. So here we know that if we're considering the circumference change from first order for orbit shifts from off momentumness, first order dispersion, this orbit shift is given by the dispersion function in the element times delta. That's what we know. That's what dispersion is. So now the source of our orbit shift is coming from the dispersion in the accelerator. So we simply replace x closed orbit by the product of delta times the dispersion function. That's what we do, and integrate over the ring. So this integral shouldn't worry us. It's, in some sense, it's shorthand for a sum of discrete terms. Element 1, a piecewise element, average some dispersion, some rho, some length ds. We sum them up. In practice, of course, we integrate over different elements around the ring. And notice this expression is linear in delta. So now what we do is we define something called a linear momentum compaction factor. Linear because it's linear in the momentum deviation. So we define alpha, and it's either called alpha sub c or alpha, depending on which textbook you read. And it's defined as the overall shift in circumference for a particle going around the ring, normalized to the ideal circumference, so the fractional shift in the path length, divided by delta. So what it means is, what alpha is telling you is if you have a momentum offset delta, it tells you the linear ratio between this delta and the resulting circumference change of a particle. That's what it's telling you. It's linear because it's linear in delta. So alpha is the coefficient linking the first power of delta to delta c over c. You could well imagine a correction to this plus alpha c prime times delta squared, so on and so forth. They're non-linear momentum compaction factors. This is a very important thing. Normally people get lazy in accelerator physics. They call it the momentum compaction factor. What they mean is the linear momentum compaction factor, and that's how they use it. So to compute alpha, we have integral around the ring in terms of the dispersion, in terms of rho, ds, the length of the element, and c is the ideal circumference. So this parameter, you compute it for a lattice, and it's a number. It's like tune. I have a well-complicated lattice, LHC. It's got a tune, 64.38, whatever it is, in units of 2 pi. We also have a number for a given ring, and this is the momentum compaction factor, and it's telling you linearly for a shift in momentum what happens to the circumference of an off-momentum particle. And this is a really, really important parameter. Momentum compaction factor is important in bold lattice design parameter, and essentially because, don't think because additional course in accelerator physics start transversely and go longitudinally, that's any less important. It's not. In fact, it's more troublesome potentially. And it's one of the factors that is really the first impact of the transverse dynamics on the longitudinal dynamics. The dispersion is telling you when particles arrive early or late in RF cavity. So it's very important. Now we can just approximate this by, if we assume you have a simple ring of radius rho, circumference is 2 pi rho. Rho is then just a constant in the integral, so it comes out of the integral, and then we're just left with the integral of the dispersion around the ring. If I just call that dispersion integral divided by 2 pi rho some kind of average dispersion around the ring, I can estimate the momentum compaction factor by the average dispersion square brackets in angular brackets, divided by rho squared. Sorry, I normalized dispersion at 2 pi, so I got the average dispersion going around the ring. So an estimate of momentum compaction factor is the average dispersion divided by rho squared. What does it mean? Well, it means a large value means the path length varies a lot for off-momentum particles. This means the particles tend to spread out when they have some momentum deviation, and it tends to lead to longer bunch lengths. Similarly, a small value means a shorter bunch length. I always think it should be called momentum dilution factor, not momentum compaction factor, because if it's bigger, you have longer bunches generally. So that's the way to think of it in your head. It's a bit of a crap name. Typically, the average dispersion is bigger than naught. We've seen that in all the plots I was showing you. Remember HERA, remember LHC? The average dispersion is +2 and not -2 meters. In these accelerators, when you have a larger dp over p, you tend to move out in the ring. That's what tends to happen. So the particles tend to orbit to the outer side of the ring. Just so in this case, we generally have positive momentum compaction factors. An isochronous lattice counters this tendency. An isochronous lattice is a lattice so designed that particles of some spread in delta p over p, have the same revolution time. Isochronous, same time. So naturally, lattices are not isochronous. They have a momentum compaction factor, but you can design them by changing the parameters such that you bring down momentum compaction factor. And you have some range of delta over which you have the same revolution time, either by construction or by twiddling parameters, either systemically by the basic design of the lattice or because it's tuned to be like that. Normally you have isochronicity to some order in delta. So you say I'm isochronous to third order in delta, which means I do have deltas of 4 non-isochronicity by particles. And you have some specification of that. So that's that, and we'll come back to this probably now next week, because on the schedule it's down to give a tutorial, whatever that means. So probably I'm going to end up finishing off the slides for most of that time. But that's okay. Then we can ask any questions at the end and stuff like that. So we'll probably come back to this next Monday, where we'll finish RF cavities and we'll think about arrival timing cavities. So that's an impact, the first example of a transverse effect, an orbit shift with momentum, on a longitudinal effect, arrival time in a cavity in the path length. So that's quite interesting. But now we come to what's called chromaticity. Now chromaticity is, we split up the motion for dispersion as the betatron oscillations plus a shift, which is linear in delta, and then we oscillated around a different closed orbit. What chromaticity is the impact of off-momentum particles on the focusing or oscillating behavior of the lattice. So it's a shift of the betatron oscillations. We're going to get this by retaining the next most interesting term in Hill's equations. We first of all just retained terms proportional to x. We got normal ideal oscillations. We then retained a term that was proportional to delta only. We got dispersion. The next most interesting term is second order. That's retaining terms that look like x times delta. So coupling longitudinal motion to the transverse motion again, and that's called chromaticity, and that's what we're going to do now. The basic idea is that the focusing of particles in an accelerator through quadrupoles depends on the momentum that they have. So I design a quadrupole and I say I want a certain k normalized gradient we saw in our Hill's equations. I need this k for this behavior. You then build a quadrupole with a certain gradient based on the particle rigidity. But in reality, you're going to send in particles of the right momentum, so the quadrupole strength's right, but you're going to send in particles with different momentum as well, and they're going to see in quotes the wrong gradient. So they're going to see different focusing, they'll have different transverse oscillations, and that's what chromaticity is. So you can see the simple example. We have a quadrupole lens here on the left. It's a horizontally focusing lens, and this is the horizontal plane, and we have a flat ray coming in, so x prime equals 0 coming in, and the blue line is the design momenta. So this is what we meant the lens to do. So we meant it to have this focal length to give us this photocell properties, this stability, this tune, that kind of thing. But in reality, a higher momentum particle is more rigid, it's harder to bend. So if this guy enters here, it's going to be bent less by the same B field it momentarily sees. So it's going to be deflected towards the axis, but at a slightly shallower angle. So it's going to come in miss the ideal focal length. You're going to get some kind of aberration going on. Similarly, if you have less momentum than the ideal momentum, you're going to be bent more by this field. You're going to come down sooner, and you're going to hit the axis there and have a shorter focal length. So chromaticity is a momentum-dependent focusing, essentially. It's the impact on your transverse focusing properties of the beam's momentum spread. So focusing is momentum-dependent, and everything that we associate with transverse focusing is momentum-dependent. That means the beta function is momentum-dependent. So the beta function we've seen so far is the on-momentum or ideal beta function. We also define off-momentum beta function. Similarly, the tune. The tune is the ideal on-momentum tune. In reality, we're going to shift the tune with momentum spread, and this is called chromaticity. So let's calculate it. Dead easy. So what we're going to do is we're going to get in the habit now of writing things, we're going to look off momentum behaviour as an expansion in delta. This is what we generally do. And I do this because a lot of textbooks don't write these equations explicitly, and it's left implied. So this is an expression for the tune. We now agree that the focusing depends on the particle momenta. So if we do have a momentum deviation of our particles, we have different focusing, different beta oscillations, a different tune in general. So the tune depends on the momenta. The question is, how does it depend on the momenta? What we do is we do an expansion. We do an expansion of the tune about the ideal tune organised in powers of delta. So the tune, see the whole in the x or the y plane, is now given by the tune for zero momentum deviation, the ideal tune, plus some shift times delta. So the tune of the machine will now shift if the particle momentum deviation shifts. The coefficient, the linear tune variation with delta, so the first term in this expansion, is generally called the chromaticity, or more precisely, the linear chromaticity. So if someone just chucks around terms and says, I've calculated the chromaticity, you say, is it the linear chromaticity, the first non-linear chromaticity, so on and so forth. So I can derive a whole bunch of terms, delta squared, delta cubed, and so on, that tell me how my tune varies with delta. In LHC and other synchrotrons, we care as much as this to third power. So we care about the non-linear chromaticity 2 levels up. So we care a lot about these quantities. So, but this course is purely linear, because that's what we would do. So we're going to study the linear chromaticity. But it's a bit of a misnomer, because chromaticity arises from the coupling of the horizontal and longitudinal plane. In Hill's equations, it's terms of x times delta. They're non-linear because it's not first order in x or first order in delta. So chromaticity is always non-linear if you look at the equation of motion. When people say linear chromaticity, they mean linear in delta in an expansion of the tune. So there's a subtlety there to be careful of. But chromaticity is inherently a non-linear phenomenon. To analyse this, we turn to the equations of motion, but now we don't chuck away terms which are x times delta. We're going to keep them. We did that before. So again, we play the same game that we played for the dispersion. We play the same game. We have this, we derived this, and we looked at it. Last time, do you remember, we wrote this as p into 1 plus delta, expanded that binomially, expanded this term, so on, and we kept the driving term, which was delta over rho. Now we're going to keep an extra term, x times delta. So we do what we did before, we expand everything out, and we keep the term x times delta we previously dropped. And actually there, that times that is x times delta. So no, it's second order in the variables, it's non-linear, but that the chromaticity has to be non-linear because it couples the 2 planes. So we expand out the brackets, we drop the terms you don't care about, and we're left with a new equation of motion. And if you do the algebra, expanding everything appropriately, you end up with this. Now, you look at that, you think, ooh, there's a lot of terms there. But actually, we understand them. Let's drop all the delta terms. That's equal to 0. That's just a normal, basic on Menton-Hill's equation. Matrices, beta functions, tune, so on and so forth. We retain the delta term. We get a driving term for dispersion. We then solve that. We get orbit shift with momentum. Good. Now the next terms come in. It's this. Which is now saying that not only do we have our standard Beatrice oscillations, we have dispersion, orbits will shift with delta, but now we're going to get focusing the change with delta as well. So we're adding in physics layer by layer by layer and getting more complicated. We've almost reached a point where we can't go any further with a linear approach. Because the next most interesting terms, if we just confine ourselves to the horizontal plane, we could have a delta. Next most interesting term would be an x squared, which will be a sextuple, which we'll do today. So we can do that, but not with the matrix approach. We could have a delta squared over rho to some power, I forget what it is. That's going to be the first nonlinear correction to dispersion, so it's how the orbit shifts with delta squared. Then we could have terms looking like x squared, delta and things like that. But it's getting really complicated then, so we won't do that. So this is the only term we're going to keep using this approach to beam dynamics, where we define this as normal, 1 over rho squared from the natural focusing of the dipoles, and g over b rho, which is the rigidly normalized quadrupole gradient. We can think of this extra complicated term actually as a quadrupole term, quadrupole field error of some strength delta. If you just look at that equation, you see the left-hand side in k was a term, was some constant times x. That was our quadrupole term. This term is proportional to x, so it looks the same, but it's like there's extra quadrupole in the lattice with this strength, but also multiplied by delta. So it's chromatic. So it's like we have a quadrupole field error with a strength that depends on delta. If you do the same thing in the vertical plane, by the way, you'll find a chromatic perturbation, chromatic term in Hill's equations, looking like this, where it's just like the homogeneous version of Hill's equations vertically, where we have no 1 over rho squared, obviously, because there's no focusing, there's no bending in that plane, but we'll have g, different sign to that, because g's positive for a horizontally focusing quadrupole, and we'll see it turn like that vertically. So we see chromaticity in both planes. Unlike dispersion, we see it in the vertical plane. So we know how to compute the effects of a quadrupole field error. We know this. We did it last week. Do you remember? We had a lattice with a one-turn map. We added in a quadrupole error via a matrix and extracted the tune shift by playing with the matrix right at the end. So if we have a lattice with some quadrupole error in, we know what happens to the tune, already calculated that. And we derived this expression, and we did derive it. If we have a lattice with a quadrupole field error in, k of s, then the shift of the tune is the product of the beta and the k field error integrated over the lattice divided by 4 pi. That's what we did last week. So actually, chromaticity for us is dead easy because it's just a quadrupole error. Okay, it depends on delta, just the first order, but that doesn't really matter to our expression. It doesn't really care. This expression doesn't care where this k comes from. So we just go ahead and compute the tune shift. So the tune shift, therefore, because of this chromatic term, is just 1 over 4 pi, beta of s, the -1 coming from that -1 there. Then we've got this slot, where that's the gradient of the quadrupole, that's b over rho, and that's delta. So that's an expression as linear in the momentum deviation. So let's just look at that in a little more detail. So what we're going to do is, we're going to define the tune shift per unit delta as a chromaticity. So that expression on the previous page was linear in delta. We're going to take the coefficient of that and call that the chromaticity. So the same way that the dispersion is the orbit shift for unit delta, the chromaticity of a lattice is the tune shift for unit delta. So if someone says to you, I've got 4 units of chromaticity in my lattice, you say, well, I know the tune shift if I'm 100% off momentum. You know it straight away. It's just the number. So the tune change per unit delta is the chromaticity is given by this in the horizontal plane and in the vertical plane. Sorry, they're both in the horizontal plane. We just ignore the dipoles. So if we have a gradient, if you have some quadrupolar gradient G and it's some beta functions, because we know quadrupoles generate focusing errors, the resulting chromaticity contribution is given by the gradient of the quadrupole times the beta function integrated over all the quadrupoles divided by 4 pi with a minus sign. Now the minus sign will come back to it. This means that quadrupoles generate chromaticity. We know that, but how much they generate chromaticity depends on the beta function. So if I've got a strong quadrupole, strong focusing, probably large focusing errors. If I happen to have that beta function, that magnitude of a large beta function, I generate even more chromaticity. So chromaticity is sensitive to where the quadrupoles are on the lattice, not just the strength of the quadrupoles. This chromaticity is natural because it arises from the quadrupoles. People talk about natural chromaticity. A lattice, a strong focusing lattice, photocells, say alternating gradient quadrupoles, has quadrupoles in it. Of course it does, otherwise it's not a lattice. Quadrupoles give you chromaticity. So natural chromaticity is the chromaticity you naturally have because you have quadrupoles. You see what I mean? Bit of a terminology there. And any lattice with quadrupoles has chromaticity. If you calculate the same thing in the vertical plane, you'll find this expression, where that's beta y, and there's a positive sign there because of the way the Hills equation structure works. So that's good. Now, either you can see this straight away, or you'll scratch your head for days to worry about it. The natural chromaticity, according to these expressions, is naturally negative in both planes. Now that's not very obvious from the equations at all, but have a think about it. But the reason is that the horizontal beta function, we had the photo lattice. Beta x was biggest in a horizontally focusing quadrupole. Okay, so we have a horizontally focusing quadrupole, that's positive, that's biggest, so we get the biggest contribution horizontally from the focusing quadrupoles with a minus sign, so overall the chromaticity is negative. In the vertical plane, we care about the vertical quadrupoles, so this is when G is negative, so G is negative, beta y is naturally biggest, so the contribution is going to be biggest from the vertical quadrupoles in the vertical plane, so it's going to be negative. Because in a vertically focusing quadrupole, if you go back to our lectures 4 or 5 weeks ago, G was negative. So you get so chromaticity is naturally negative in both planes. Not a very intuitive result, but it is. Now we define the linear chromaticity as Q. So delta Q is Q prime times delta, and you can show for a fun little calculation, look in the textbooks, in the same way we had beta function and dispersion results for a photocell. Also, we can extract an expression, analytic expression for the chromaticity in a photocell, and it's the horizontal chromaticity is given by the difference in the beta functions in the two quads divided by 4 pi times the focal length. I've not derived that, but that's just to show you can derive expressions for chromaticity in photocells should you be that way inclined. So what does it mean? Well, there's expressions of chromaticity. It's generated in quadrupoles, and it gives you a tune shift, linear in delta. That's what it does. What does it mean? Well, what it means is we design an accelerator so that it has some tune. And do you remember when we looked at dipole and quadrupole errors, we saw the resonance terms, the 1/over sines bits prefactoring the orbit shift and the tune shift for quadrupole and dipole errors. Which means, and we stated we have resonances, that if the tune goes onto an integer, or onto a half integer, then we have problems with resonances. So the tune has to be tightly controlled. So if I design an accelerator, I have to, my chromaticity will shift my tune, and I might shift the tune onto a damaging resonance. So I have to control the chromaticity very carefully. And this can be very hard to do. If you look at the LHC, back to the LHC, generally we have the interaction point here, so the betas are coming in. We have a mini beta principle, so they rise quadratically in this drift into the strong quadrupoles that turn the betas over to give you the focusing. So these quadrupoles here are strong quadrupoles, and because of the mini beta principle, the betas got very big. So they generate a lot of chromaticity. And in fact, the LHC is 27 kilometers long, filled with quadrupoles. Half of the chromaticity in the LHC arises from these structures around the interaction points Lattice and CMS. So it's a big problem for us. So when you design the LHC, you have to control your chromaticity to keep the tune at a very at the correct point. So why is it bad? I'll show you some cool plots now. So chromaticity is made by any focusing lattice. You have quadrupoles, you have non-zero Ks, you have gradients, you generate chromaticity. And it tends to be negative in both planes. So there's an expression for it. So there's the gradient of the quadrupoles in the lattice, there's the beta, there's B rho. And so it tells you how much the tune shifts for a unity shift in the momentum deviation. So this is the bad bit. The beam has an energy spread. So the beam is not just one particle, it's billions and billions of particles. Each of them has its own momentum deviation. There's a spread. That means that a given particle has its own tune, which means the tune, the beam, is not a single tune. So I wrote down the photocell, so we built that accelerator, and I said the phasor bands per cell in my photocell is 45 degrees. If I have lots of these things, in a ring, it's a certain one-turn tune, one-turn phasor bands. But the tune is not a unique thing. It's a blob in tune space because of the momentum spread in my beam. So it means that there's not one unique tune, there's a whole bunch of tunes. And if you imagine your beam in tune space, horizontal and vertical tune, you're not a dot, you're a big fat blob. And that blob is proportional to the chromaticity and proportional to the momentum deviation spread of the beam. And that's bad because we could be touching these resonances that would give us bad orbit deviations and bad tune shifts and such things. We saw that last week, 3 weeks ago, when we calculated the tune shift for the quadrupole error, and that's bad. So we have to control chromaticity because we want to make sure the tunes of the beam don't go anywhere bad in tune space. This is very important. There are more reasons than this, but this is the first and foremost reason. So here's a diagram. This is Hera, the electron-proton cloud we talked about at DESI. Horizontal, vertical plane. And you get these tune measurements just by having some kind of beam pickup and Fourier transforming, looking at the frequency spectrum of the beam. So that's at horizontal, that's at vertical, and that's at units of 2 pi. And you only see the fractional part in these kind of tune measurements. So that's the horizontal tune, and that's the vertical tune, where this cross is just finding the biggest peak and reporting what the tune is. But if you look, if this is frequency, and this is the result of our Fourier transform, you see it's not a lovely defined single spike. It's a pale, flat thing with lots of different frequencies going on in the beam. Now this is because we designed the Hera lattice to have some tune, but it's made of quadrupoles, they're chromatic, we have some momentum spread, each particle has its own tune, and we get this spread of tunes. And the chromaticity is uncorrected in these plots. This is the point of these plots. So we're getting this big splodge in tunes across the beam, loads of different frequencies present, Fourier transform the beams pick up, and we see everything. Bad. Now, imagine we could correct the tune. We get this. Imagine we could correct the chromaticity of the lattice so that we can never stop the fact that particles have different momenta. That's just basic physics. In fact, it's a very fundamental principle called Louisville's principle. But we can reduce or correct the chromaticity induced by the quadrupoles using other elements. If we did that, then the spread of tunes in the beam will narrow towards a design tune. So again, we correct the tunes in the Hera beam using something called a sextupole, and I'll explain how this works. And look what happens to the tune spectrum. It's now a much more nicely defined peak with a much more well-controlled localized tune. So that's the uncorrected chromaticity, big splodge of frequencies, corrected chromaticity, much nicer. Now, there are many reasons why corrected chromaticity is good. One is the beam going onto resonances. And another is aperture in some accelerators. If you have different focusing errors, I've not derived it for you, but you can calculate what this means to the perceived beam size in your accelerator, and it can touch apertures. Third reason is instabilities, which is way beyond this course, where if you have chromaticity, you can drive certain resonant beam instabilities. So controlling chromaticity is very, very important. But the basic reason is to control the spread of tunes in the beam. Right, so how do we do this correction? Well, so this is pretty amazing. You can see the frequency spectrum collapsing to a much more nicely defined peak. Now, chromaticity basically comes about when a slightly off momentum particle sees a different quadrupole field than it should do, than we intend it to. And this particle is focused differently to its friends in the bunch. Not so good. So what we need to get rid of this effect is a pair of glasses for the beam. We need a correcting device that has a different focusing for different momenta to undo the inadvertent momentum-dependent focusing that's just received in the quadrupole. That's what we need. We need a device that gives us momentum-dependent focusing. We can adjust it, if we're clever, to undo the momentum-dependent focusing we see in a quadrupole. And unfortunately, such a magnet exists, and it's called a sextupole. So, what's a sextupole? Well, a quadrupole is an element where the field, transverse field, rises linearly with transverse offset. So the next logical, in fact, stronger than that, the next term in our multipolar expansion is going to be a quadratically rising field. So we have this. Imagine we have an element where the bx goes as sxy, and the by goes as some strength divided by 2x squared minus y squared. That's a quadratically rising field, which will give us what we need, where this is some Taylor coefficient from the Taylor expansion of some arbitrary field. It looks like this funny form because of Maxwell's equations. It has to obey Maxwell's equation. Can't have any arbitrary B field. You have to obey Maxwell's equation. It has to be curl-free. So it has to have this very special form. So it's quadratic in x and y in by. So we're going to get some horizontal effects going on, which is pretty good. Note also that for the first time we've seen a term with x and y appearing in it. So for the first time ever, all the time, I think, well, he never mentions the vertical plane. It's all two-dimensional matrices, stuff like that. That's because Hill's equations, they were totally decoupled. The motion was independent. So I didn't need to. You just get the equations for the other plane by just flipping a few minus signs over. Work through it, you'll see how it works. But for the first time, we've seen an equation with x and y in. So this is the first time we'll see transverse coupling in our lattice, which is generally a bad thing. We have to generally correct it and deal with it. But we don't want that bit. We want the quadratic bit. So I've said that. So what happens is off-momentum particle passes through the sextupole, has a displacement. So imagine we have a particle going into a sextupole. It has some Beatrice oscillation. It has some offset from dispersion because there's dipoles in the lattice, and it's got some vertical coordinate from vertical Beatrice oscillations. There's no vertical dispersion because we're only bending in the horizontal plane. So that's some arbitrary particle coordinate. What fields does this particle see? Well, the beta x is just, sorry, the bx is just the x and the y coordinates multiplied together. That's x and that's y. If you multiply this out, we get terms that go like x beta, y beta. That's a coupling term. We've got a term that goes as the sextupole strength, the horizontal dispersion, the momentum deviation of the particle, y beta, and do the same in the y motion, and we get a whole bunch of terms looking like this. There are loads of them. I won't go into them all, because each one in itself is a whole study. But there are some handy ones here. Notice, by the way, we've got fields that go as delta squared, so we've got some non-linear dispersion coming in for the first time, so that's way beyond this course, but you can see where it arises. But there are many terms here, some good, some bad. The helpful ones to us are these, because we get horizontal dispersion, some delta, and y beta, horizontal dispersion, some delta, x beta. So the horizontal dispersion function has made the sextupole into a quadrupole with an effective gradient, SD, the strength of it. That's a bad notation, that should be S. Oh, sorry, no, it is D. S times D times delta. So what's a quadrupole? It's a BX with a BX that depends on Y, or it's a BY that depends on X. It's a linearly increasing field. So this BY does increase linearly in X, but it's got a gradient, S times delta times D. See the point? So we've created a quadrupole magnet with a sextupole. Well, it's got a linearly rising field, and the gradient of that linearly rising field is the product of the sextupole strength, the horizontal dispersion, and the momentum deviation. That's just what we need. So we actually can use this to cancel the natural chromaticity of the lattice. So what dispersion does, it effectively makes the sextupole into a quadrupole with a momentum-dependent focusing gradient. This is probably the hardest thing that we do in this whole set of lectures. So it's very fundamental to storage rings. So what we can do is we can compensate the chromaticity in the ring with sextupoles. So your logic is I design a photocell. I want to keep the beam tightly focused. I have quadrupoles. I alternate in both planes. It goes through nicely. But I've got a tune. But I'll generate chromaticity. I then need to add sextupoles to my photocell to correct the chromaticity generated by the quadrupoles and make sure my tune is not a blob in tune space. So I can undo the tune shift from the chromaticity by adjusting the sextupoles. Now, I've glossed over this. It's not really this simple. It's quite a complicated procedure to adjust your sextupoles. It'll take ages to explain the precise thing, but you see the point, the fundamental principle, that you adjust the sextupoles to achieve a momentum-dependent quadrupole term to cancel out the fields. Sounds good, but it's not really, because we ignored plenty of terms in the field of the sextupoles. Then there was a whole bunch of them. Some were good and fixed the chromaticity. Some are bad and introduce nonlinearities and coupling into our accelerator, which are generally bad things. That's the last time I will hear a sextupole today, at least from me, because this is a very, very introductory course on linear dynamics and sextupoles, because the field goes as x squared. The moment I add a sextupole field to my Hills equations, I get a nonlinear equation, because it goes as x squared. It has to be, or xy, or y squared. And you can't use matrices, and you have to do a much more sophisticated approach to solve them. So often what people do, is they use particle tracking. So they would design a lattice linearly, they would adjust the sextupoles to correct the chromaticity, then what we call in accelerator physics track the lattice, which is kind of this catch-all term for ray tracing of particles through accelerators. Now you have to be really careful here because it's very difficult to solve these equations of motion non-linearly exactly. You have to make some approximations. So every tracking code you ever see has an approximation for how the particle evolves. You need to understand what that approximation is. But if you manage to do it, you can start to track particles and you can just move through the lattice and understand particle motion. What this leads to is the study of the machine's dynamic aperture, which is essentially the regions in, this is position and x prime phase space, where we have stale motion over many, many turns. Essentially our ellipse we had 4 or 5 weeks ago for the linear motion has become something like this, where here, for small amplitudes of particles, we have our ellipses. They're circles because we've made a transformation into a space where ellipses become circles for ease of calculation. If I just transform x and x prime to something else, I can make my ellipse a circle. It's just a bit nicer. So they're my ellipses, nice, stable, regular motion. But as I get larger in amplitude in x or x prime, crazy stuff starts to happen. And this stuff is because of nonlinearities in the lattice. But this is well beyond this course. But you can start to see what would happen. So provided I stay nicely, happily in this region, I don't really care what happens there. I oscillate around there with some tune. But as I get to larger, crazy stuff starts to happen. And that'll be in a future course. So then we have this slide on lattice design. 3 weeks ago, something like this, where the top bits were big and the bottom bits were small. And the top bits we talked about. We talked about building a photocell, choosing the dipole strength, matching the lattice, maximum field strengths, that kind of stuff. Now we have these last three things you have to do for your lattice. The first is to get stable solutions of momentum particles. You have to add in sextupole magnets and also RF cavities, but I haven't done that yet. These give you nonlinear fields to control things like chromaticity and give you a very, very good stable motion, even for some momentum deviations. Once you correct the chromaticity in step 9, these strong fields add in extra terms to your beam dynamics that you need to study normally with particle tracking, to understand the behaviour of the lattice. This is quite hard and quite laborious. Tracking is a slow process. Because you've given up your analytic approach, it becomes more of a black box. You get odd results out. It's all a bit confusing. You get resonances you don't expect to see. This is very tough, this bit, but this is what a lot of the serious work in designing a new lattice is. Linear optics is not so hard. What is hard is chromaticity correction and long-term tracking and such things. In a real machine, there's then imperfections, which we then talk about. We have power supply fluctuations, we have alignment errors, we have ground motion. We have to then correct these things. So so far we've seen two things. We've seen the impact on the orbit of the dipole error, and we've seen a stray quadrupole field giving a tune shift. Those things have to be corrected. Also everything else does, power supply ripples, ground motion. So what we need is we generally add two things to our lattice. One, diagnostics. For example, for the orbit, we have BPM, position monitors, to know where the beam is. And then we have extra dipoles, dipole correctors, that see what happens in these BPMs and somehow feed back to correct the orbit to what it should be. The same goes for tune, the same goes for coupling. This is what these guys are for, skew quadrupoles, correct coupling on the lattice. So your basic lattice, the ideal lattice, even with non-zero delta, still has a whole bunch of things to worry about before it can ever work. And a lot of this stuff you actually have to build the machine to really understand them. So I've gone a bit slow today, so I think next week will just be a whole lecture on the tutorial. That's probably okay. Right, so the next topic, I've got 2 slides on. I think it's 2 slides. But it pains me a little bit. I only have 2 slides in it, but it's a very important topic. And it's called admittance of the beam. So you remember that we derived really ages ago in the current Snyder formalism an invariant attached to a single particle. I call it epsilon. I call it single particle emittance with a big warning, because really it should be called something called the action, which is you have to use a Hamiltonian to really understand. So, but the point is that we define the emittance of a particle, which is the constant in our current standard analysis. So the motion of an individual particle is specified completely by its emittance and its initial phase. Remember that in the current standard formalism. The reason why single particle emittance is a bad word is that people in the field generally use emittance to describe the bunch as a whole, not at the particle by particle level. You have to be a little careful. So different particles have different emittances and different phases, but they all have the same current Snyder functions, alpha and beta. Actually, that's not true, because, well, I'll let you figure that out. But the beta function does depend on the particle, because, well, I'll tell you the answer, because they have different momenta. So my particle X has momenta 1, it sees different focusing, it has some beta function. So beta function itself depends on momenta, so you have to be a little bit careful. But normally people say beta functions on momentum beta functions. So the ideal particle, i.e. the particle with x prime equals y prime equals 0, has 0 emittance and will stay there forever through the accelerator, just in the middle of every magnet. That's the ideal particle. But we always have more than one particle in our beam, hopefully. So we have to understand how to characterize a beam of particles. Each one has its own emittance. And this is a very overviewy slide, because I just want to flag this up, because it's a lecture in itself to go over this. So in general, we have more than one particle in the beam, each with its own value of the emittance. So can these plots be made? This is x versus x prime at different points in the accelerator. So you can see the splodge of particles. This is actually going through a photocell. The particles at position 1, position 2, 3, 4, 5, 6, 7, 8, 9, 10. So this particle there transforms to there, transforms to there, transforms to there, and so on and so forth. So you have to splodge. And you can see it's following the ellipse, right, roughly. And in fact, each particle has its own emittance, so each particle is following its own ellipse with conserved area. So what we have to do is we choose one of the particle's emittance to represent the emittance of the entire beam. That's what we generally do. So we draw on some kind of defining ellipse. This is slightly hand-wavy, but there's a better way at the bottom. This is what some people do, though. They pick some ellipse and they say this particle's emittance encompasses 39% of the beam. I'll use this emittance to describe the beam's emittance. So they have some definition of their emittance. And the emittance is one of the most confusing things in this field because every single person defines it in a different way. And you have to check what they use their definition. The LHC people have a definition. People who have light rings have sort of definition. If you go over the road, they've got a definition. Always check what the definition is. So you could say, for example, I want one number to characterize this beam distribution. So let's look, take the stylized picture. This particle has some emittance which corresponds to this area of this ellipse. That particle's got a bigger area of its ellipse, and they're all just going through the accelerator. Now, I'll pick this yellow one's emittance to represent the emittance of the entire beam, because it encloses a certain number of particles inside it, and I use that to describe the whole beam. So and that's what we do. For example, we can pick the emittance of a particle which 95% of the beam particles are inside that ellipse, and that'll stay true because area is conserved, so it has to stay true. So that's one definition, but it's worth checking. Another useful definition, again, I'm skipping over this ultra fast, so I encourage you to go and look at textbooks on emittance. When have some complicated distribution in phase space is the Rms emittance, which we find by averaging over the beam distribution. So if I have a bunch of x's, a bunch of x primes, I take the moment, second moment of x, second moment of x prime, subtract the cross moment and root it. And that gives me what's called the Rms emittance. These two are clearly related for certain beam distributions. Again, that's beyond this course. So the point, though, is that emittance is quite confusing. Find out what the definition is that your particular accelerator or project is using for the emittance. That's my tip. Finally, I'm now a whole lecture behind you now, which is not ideal, but okay. Right, on Louisville's theorem. Again, we don't have time to talk about this. It pains me that we don't. But the point is that this is Louisville. The density of points representing particles in 6D phase space is conserved if any forces are conservative and differentiable. Rather a mathematical statement. But what it means is that radiation, this is not true for radiation, but it is true for magnetic forces. So that means that if I have an accelerator with just electromagnetic fields, the density of points in phase space is a conserved quantity. I'll just tell you what this theorem is, so you'll hear it in other lectures and stuff. But the point is that the density of points in phase space is conserved. This is probably the most important theorem in all accelerator physics, and I won't tell you about it, which is probably a bit perverse. But also a point is that for the theorists among you, I've talked about position and angle being the coordinates of my particle. If you know Hamiltonian dynamics, you know I can't do that. I've got to take position and momenta. So I've used xx prime in phase space, and really should use x and p. That's a slight technical point. Some people in this field call this a trace space and not a phase space. Acceleration, which we haven't discussed yet, keeps the density of points in xp phase space constant, but phase space in xx prime actually reduces under acceleration. So you'll come across something called adiabatic damping in a different course, where when you accelerate, the beam emittance decreases. And you go, well, how the hell can that be because of Louisville? Well, look, so this is another aside. Louisville applies to xpx space, not xx prime space. That's what will happen. Right now you're thinking, what the hell is he talking about? One day you'll thank us when you get puzzled over adiabatic damping and you remember what I said today, and that will resolve your puzzlement. Finally, there'll be other courses from the Cockcroft on other approaches of doing dynamics and Hamiltonians. They have a thing called symplecticity, which is deeply linked to Louisville's theorem. Again, this is beyond this course, but I'll make this point that our transfer maps have unit determinant. That's equivalent to symplecticity in our system. This slide's quite confusing. I put it in so you've heard some words like Louisville's theorem, trace space, this kind of stuff. So other courses you'll link back to it. Right, it's 1:45 now. We still have to do longitudinal phase space. On the schedule, it says tutorial next week. Now, what I suggest we do is we just discuss longitudinal phase space in an informal setting, something like this. So we also can discuss any of the problems that I've set through the lecture notes if you want, best email me first. I'll just make sure I know how to do it before we discuss it, and then we can talk about it if you want. But I've got enough material for the whole lecture if we so want. So we'll just decide next week what we do. All right. Thanks very much, everyone.
Yeah, I got the email.
What's on it? Yeah. Not in there.